At 17:05 Universal Time yesterday, a sensor 35,786 kilometers above the equator counted 1,160 of a particle that passes straight through the wall of a spacecraft. The alert threshold is 1,000. It had already been crossed the day before, and unless you fly satellites for a living, nobody told you, because this is the one space weather hazard with no public warning scale at all. Every scale that does exist read 0 yesterday, while the particles named in the loss of a $200 million satellite quietly filled the space our communications run through. So what is up there? And what is it doing to the hardware that everything else depends on? If you want the stories happening above us that never make the news, hit like and subscribe. Drop a comment telling me where you're watching from and whether you have ever lost a satellite signal and never found out why. Now let's get into it. Part 1. The number that crossed a line. Nobody watches. At 17:05, Universal Time yesterday, a sensor on a satellite parked 35,786 kilometers above the equator recorded a number, and that number was 1,160. The satellite is called GOES-19. It belongs to the National Oceanic and Atmospheric Administration, and one of its jobs is to sit in geostationary orbit and count the particles going past it. Not all particles, a specific kind. Electrons carrying more than 2 megaelectron volts of energy, which is a technical way of saying electrons moving at a large fraction of the speed of light. The unit it reports them in is called the particle flux unit, and yesterday afternoon the count came in at 1,160 of them. The threshold is 1,000. When that line gets crossed, a message goes out automatically. It is not a press release. It has no headline, no illustration, no forecaster's name attached to it. It is a block of plain text with a product code, and the product code is ALTEF3, and yesterday's message carried serial number 3721. It says the threshold was reached at 15:34 Universal Time. It was issued 1 minute later, at 15:35, and at the bottom there is a comment field, and in that comment field somebody's software had written a single line. Yesterday's maximum, 1,077. Read that again, because it is the part that changes the shape of this story. The threshold had already been crossed the day before, 1,077 on the 25th of July, 1,160 on the 26th. 2 days running, the count of high-energy electrons in the space where most of the world's communications satellites live went above the level at which the people who operate those satellites are formally told to pay attention, and nobody told you. I want to be precise about what I mean by that, because I am not accusing anyone of anything yet. The alert exists. It is public in the sense that anyone can go and read it if they know the address of the server it sits on. What I mean is that it did not enter the world the way space weather normally enters the world. There was no color-coded graphic. There was no probability forecast on the evening news. There was no aurora photograph, because this particular phenomenon does not produce one. There was no scale. That last part is the thing I've not been able to stop thinking about since I started pulling this data apart, and it is the thread that runs through everything that follows. Every space weather hazard that can reach down and touch a human being has a public warning scale. This one does not, and by a long way this one has been implicated in more damage to commercial spacecraft than any of the ones that do. Let me put the geography in front of you first, because the numbers only mean something once you can see where they are happening. Earth sits inside a magnetic field, and that field is not a smooth shell. It is a shaped thing, squashed on the side facing the sun, drawn out into a long tail on the side facing away, and inside it there are regions where charged particles get trapped. They spiral along the magnetic field lines, bouncing from one hemisphere to the other, drifting slowly around the planet, and they do not leave. Those regions are called the Van Allen radiation belts, after James Van Allen, whose instrument aboard Explorer 1 found them in 1958. There are 2 of them, an inner belt, closer in, dominated by protons, and an outer belt further out dominated by electrons. Geostationary orbit is at 35,786 kilometers. That is the altitude at which a satellite circles the Earth in exactly the time it takes the Earth to turn once, which is why a satellite dish on the side of a house can be bolted in place and never moved again. It is the single most commercially valuable ring of space around this planet. Television distribution lives there. Telephone backhaul lives there. Maritime and aviation connectivity. Financial timing signals, broadcast feeds, and a great deal of government communication all live there. And geostationary orbit sits inside the outer electron belt, or right at its edge, for much of the time. That is not a coincidence of framing. That is the whole engineering problem. We put the most valuable hardware we own in the middle of a population of particles that is constantly changing, sometimes by factors of 1,000 or more over the course of a few days, and then we hope the shielding holds. Yesterday, that population was above its alert threshold for the second day in a row. Here is what makes it stranger. If you had looked up any of the ordinary indicators yesterday and today, you would have concluded that space was having one of its calmest stretches of the month. I will go through those indicators properly in a moment, because the contrast is the story. But the headline version is this. The geomagnetic field is quiet. The solar wind has dropped back to a sleepy 366 kilometers per second. The aurora is running at about a quarter of the power it needs to be interesting, and every one of the 3 public space weather scales is reading 0, 0, 0, 0, and 1,160. There is a name for the particles doing this, and it is not a name that scientists chose to be dramatic. In the literature, and among the engineers who work with them, they are called killer electrons. That is the actual term. You will find it in peer-reviewed papers. Somebody, at some point, needed a shorthand for the electrons in the outer belt that are energetic enough to kill spacecraft, and the shorthand stuck. And now it sits in journal abstracts looking like something out of a film poster. They earned it. I am going to spend a good part of this walking you through exactly how. Because the mechanism is genuinely strange, and it is not what most people assume when they hear the words radiation and satellite in the same sentence. It is not that the particles overwhelm the electronics with a flood of energy. It is not a bright flash of damage. It is slower, quieter, and much more unsettling than that. But before the mechanism, I want you to sit with the structural fact, because the structural fact is what makes this worth an entire investigation, rather than a footnote in a forecast. There are 3 public space weather scales. They run from 1 to 5, exactly like hurricane categories, and they were designed that way on purpose, so that a person with no scientific training could look at a number and know roughly how worried to be. G is for geomagnetic storms, the ones that light up the sky and push currents into power grids. S is for solar radiation storms, the ones that matter to astronauts and to aircraft flying polar routes. R is for radio blackouts, the ones that knock out high-frequency communication and degrade navigation. G, S, and R. Those are the 3. There is no scale for the particle population that has been named as the probable cause in the loss of a $200 million communications satellite, in the failure of the 2 spacecraft that carried Canadian television and Northern telephone service, in the end of a Japanese Earth observation mission carrying $150 million of NASA instrumentation, and in an 8-month episode in which a live satellite drifted uncontrolled through the geostationary belt broadcasting at everything it passed. There is a threshold, there is a bulletin, there is a mailing list. That is it. Now I want to be honest about something, because this channel does not do the thing where a gap in a system automatically becomes a conspiracy. There is a perfectly boring explanation for why no scale exists, and I will give it to you in full later, and it fits the facts better than anything else I have found. But the boring explanation does not make the situation less interesting. It makes it more interesting, because it means this hazard is invisible to the public, not because anyone hid it, but because of a categorization decision made decades ago about who space weather warnings are for. The consequence is the same either way. There is a storm going on above your head right now that does not appear on any map you have access to, and there is one more thing about it which I will come back to again and again, because it is the property that makes this whole subject so difficult to see clearly. The damage does not happen when the storm happens. Something else entirely has to occur first. Part 2, the 3 scales and the one that was never built. Go and look at the space weather page you would land on if you searched for it tonight, and you will find a small coloured panel in the corner with 3 rows in it. The top row is R, and today it reads none. The middle row is S, and today it reads none. The bottom row is G, and today it reads none. Under each one there is a probability for tomorrow and the day after, and today those probabilities are modest. Something like a 45% chance of a minor radio blackout, a 5% chance of a radiation storm, and no expectation of a geomagnetic storm at all. That panel is the entire public interface to space weather for almost everyone on Earth. It is what gets scraped into apps. It is what television meteorologists glance at when they want to mention the aurora. It is the thing that turns a physics problem into something a person can act on. And it has 3 rows, because in the middle of the 1990s somebody had to decide which space weather effects belonged on a public scale, and they decided on the basis of who gets hurt. Look at what the 3 scales actually measure, and the logic is obvious. G, the geomagnetic scale, is about currents induced in long conductors and about the aurora. Its effects are listed in terms of power grids, pipelines, and how far south you can see the lights. Those are things that happen to the general population. S, the radiation scale, is about energetic protons, and its effects are listed in terms of radiation exposure to astronauts and to passengers on high-latitude flights, plus damage to satellite electronics from single-particle strikes. Human bodies again. R, the radio blackout scale, is about the ionization of the upper atmosphere by X-rays, and its effects are listed in terms of high-frequency radio and low-frequency navigation, which matter to aviation, shipping, and emergency services. Every one of those 3 scales is built around a question that ends with a person. The relativistic electron flux does not end with a person. It ends with a component. It ends with a coaxial cable inside an amplifier inside a satellite, and the person it eventually reaches is somebody whose television feed drops out, or whose ship loses its data link, or whose bank's timing signal goes slightly wrong, and by the time it reaches them, the chain of causation is so long and so private that nobody will ever connect the 2 ends of it. So the electron hazard got a different kind of product. It got an operational alert, addressed to the few hundred people on Earth whose job involves flying spacecraft delivered in machine-readable plain text with a number in it and nothing else. No severity level, no advice, no forecast graphic. Just, the threshold was reached. Here is when, here is yesterday's peak. I've been staring at that alert for a while now, and what strikes me about it is how completely it is written for someone who already knows. It assumes the reader knows what 2 megaelectronvolts means. It assumes the reader knows what a particle flux unit is. It assumes the reader knows why 1,000 of them is the number that matters and not 500 or 5,000. It is not communication. It is telemetry with a courtesy notification attached. Which is fine, if the only people affected are the people on the list. But we have built a civilization on top of the hardware those people fly, and we did it fast, and most of us have no idea how much of ordinary life now routes through a few hundred boxes in a ring above the equator and several thousand more in low orbit beneath them. When one of those boxes dies, the failure notice does not say space weather. It usually does not say anything at all, because the operator is under no obligation to tell anyone, and there are commercial and insurance reasons not to. That is the part where people start reaching for a conspiracy, and I understand the instinct. A hazard nobody publicizes, damaging hardware whose failures nobody has to report. In a domain most people cannot observe for themselves. If you were designing something to look like a cover-up, you would design that. I do not think it is one. I think it is something more ordinary and in a way harder to fix, which is a system that was set up to warn the public about the things that hurt the public, quietly failing to notice that the public has since become dependent on things that do not get hurt in a public way. Let me make the contrast concrete, because I think it lands better as a comparison than as an argument. When a large sunspot fires an X-class flare, you will hear about it. There will be a number, there will be an R rating, there will be a map of the sunlit half of the Earth shaded to show where radio was degraded, and the whole thing will be resolved within hours. The flare happens, the X-rays arrive 8 minutes later at the speed of light, the ionosphere thickens, the radio goes bad, the ionosphere recovers, the radio comes back. Start, middle, end. It is a story with a shape. When a coronal mass ejection is on its way, you will hear about that too, and you will hear about it for days, because the travel time is 1 to 3 days and every hour of that is forecastable and coverable. There will be arrival windows, there will be aurora maps, there will be a G rating, and again, it will resolve. The cloud arrives, the field shakes, the sky glows, the storm subsides. Now try to tell the electron story the same way. The flux started rising some days after a stream of fast solar wind arrived. It went above threshold. It stayed there. The stream that caused it has already faded and the flux is still elevated. It will decline over the coming days. Somewhere in the next 2 to 3 weeks, a component on some spacecraft in a place nobody can point to may accumulate enough buried charge to break down, and if it does, the operator may or may not notice, may or may not attribute it correctly, and almost certainly will not say so publicly. There is no moment, there is no arrival, there is no aurora, there is nothing to photograph. Journalism needs a moment, human attention needs a moment, and this hazard does not have one, which is why an entire category of damage to the infrastructure holding modern communication together has been running for decades in a kind of public blind spot. I said earlier that I would come back to how strange the timing is, and this is the right place to start because the timing is genuinely the strangest part. The electrons that crossed the threshold yesterday were not accelerated yesterday. They were energized over a period of days by a process that began when a stream of fast solar wind reached Earth around the 21st and 22nd of July. That stream has now decayed. The solar wind speed has fallen from something like 550 kilometers per second down to 366. The driver is gone. And the forecast for today, written by the Space Weather Prediction Center in language you would need a decoder for, says the electron flux is likely to reach high levels today as the coronal hole high-speed stream effects diminish, as they diminish, not while they peak, as they fade. That sentence is the beginning of the mechanism, and once you understand why the effect outlives the cause in this system, you understand why nobody can forecast it properly, why the damage cannot be pinned to an event, and why a satellite that dies on a perfectly calm Tuesday in the middle of August might have been killed 3 weeks earlier by something that was never on the news. But to get there, we have to go back to the sky above us right now and look at just how misleadingly peaceful it is. Part 3, The Quietest Sky, in a month. Every number that the public sees today says the same thing, and the thing it says is nothing is happening. Start with the geomagnetic field, because that is the one most people have some feel for. The measure is the planetary K-index, the KP, a number from 0 to 9 that describes how much the Earth's magnetic field is being shaken by the solar wind. It is a logarithmic scale, so each step up is a substantially bigger disturbance than the last. KP5 is the threshold for a G1 storm, the weakest official geomagnetic storm level, the one where aurora starts creeping into the northern tier of the United States. Over the past 24 hours, the greatest 3-hour KP observed was 2. 2. Not close. 2 is the magnetic field of a planet doing very little at all. The individual readings behind it are, if anything, quieter than that headline suggests. 0.67, 0.67, 1.33, 1.67, 1.2, 1.33. Those are the observed values through the night and into this morning. The forecast maximum through the 29th of July is 3.67, and the official rationale says it plainly. No G1 minor or greater geomagnetic storms are expected. No significant transient or recurrent solar wind features are forecast. Now the solar wind itself measured at 1321 universal time today, 366 kilometers per second. Slow. Typical quiet conditions run somewhere around 300 to 400, and a high-speed stream will push it up past 600 or 700. We're at the bottom of the ordinary range, on the way down from something faster. The magnetic field carried in that wind is 5 nanotesla in total strength, and the component that actually matters, the north-south component called BES, is at +1 nanotesla. Positive means northward. Northward means the interplanetary field is pointing the same way as Earth's field at the point where they meet, and when that happens, the two do not connect efficiently. The magnetosphere stays closed. Energy stays outside. The official assessment in the data reads, in 3 words, northward, not geo-effective. Auroral hemispheric power, which is a direct estimate of how much energy is being dumped into the upper atmosphere at both poles, is 14 gigawatts in the north and 14 gigawatts in the south. Active conditions start somewhere around 50. We're at roughly a quarter of that. The classification attached to the number is the word quiet. Proton flux, the thing the S-scale measures, is at background. The greater than 10 mega-electron-volt channel is reading 0.263 particle flux units, with a 24-hour peak of 0.322. For comparison, an S1 minor radiation storm begins at 10. We are 2 orders of magnitude below the first rung of the ladder, and the forecast probability of an S1 on any of the next 3 days is 1%. And the 3 public scales, as I said, are 0, S0, G0. If you were writing a space weather summary for a general audience today, the honest version would be 4 words long. Nothing to report, everyone. except that in the outer radiation belt the flux of relativistic electrons crossed its alert threshold yesterday for the second consecutive day, and it is forecast to stay high today. I find this genuinely one of the more unsettling juxtapositions I've run into doing this, and I want to explain why, because on the surface it sounds like a technicality. 2 systems, 2 different measurements, no contradiction. And that is true, there is no contradiction. Everything I have just described is consistent, understood, and unremarkable to a space physicist. The unsettling part is what it means for anyone who is not a space physicist. It means the indicators we have made public are not measuring the hazard that has historically done the most damage to the systems we most depend on. They are measuring the hazards that were most visible when the scales were designed. Someone checking the space weather today, doing everything right, using the official sources, reading them correctly, would come away with an accurate impression of the aurora, an accurate impression of the radio conditions, an accurate impression of the radiation exposure on a polar flight, and no impression whatsoever of the one thing that is actually elevated. We have always assumed that if something dangerous were happening above us, the warning systems would say so. But what if the warning system was built for a different danger, and the danger changed underneath it? There is a version of this that goes wrong, and I want to head it off because I have watched this channel's comment section for long enough to know exactly where a certain kind of viewer is about to go. Nothing is broken today. No satellite has been reported lost. This is not a story about damage occurring in front of us. It is a hazard elevation story, which is a much less dramatic thing, and I would rather tell you the less dramatic true version than the more dramatic false one. What is actually happening is that a population of particles which has, on the record, been implicated in the loss of several major spacecraft is running above the level at which spacecraft operators are told to take notice for the second day in a row, at a moment when every public indicator says the sky is calm. That is not an emergency. It is something arguably more interesting than an emergency. It is a demonstration, in real time, of a gap in what we can see. Let me widen the frame for a second, because the gap is bigger than one alert on one day. The number of active satellites around this planet has risen by something like an order of magnitude in the last 10 years, driven almost entirely by large constellations in low orbit. There has never been anything remotely like this, many objects containing insulating materials sitting inside Earth's particle environment. The environment itself has not changed much. What has changed is how much of it we have filled with hardware, and how much of ordinary life now depends on that hardware continuing to work. And in the middle of that expansion, the hazard most closely associated with slow, cumulative, unattributable spacecraft damage remains, the one hazard with no public scale, no forecast graphic, and no name that anybody outside the field would recognize. I tried an experiment while putting this together, and I would encourage you to try it yourself because it makes the abstraction concrete in about 90 seconds. I went looking for the electron data the way an ordinary person would. I opened the main space weather page. I found the 3 scales, the aurora forecast, the solar wind plot, the X-ray plot, the KP bar chart. All of it useful. All of it clearly presented, none of it mentioning electrons at all. To find the number I have been talking about, you have to know that it exists, know what it is called, and know where the product lives. It is there. It is public in the strict sense. But it is public the way a filing cabinet in a government building is public, available to anyone who already knows which drawer. And when you do find it, what you get is a plot with a line on it, and a horizontal marker at 1000, with no explanation of what happens above the marker, because the people the plot was designed for already know. There is a version of this that is entirely fine. Specialist data is specialist. Nobody needs a public dashboard for every parameter a forecast center tracks. My problem is not that the plot is technical. My problem is that this specific technical plot is the only public representation of a hazard with a body count in the tens of millions of dollars per incident, and everything sitting next to it, presented in bright colors with plain language explanations, is describing effects that on a day like today amount to a slightly degraded shortwave radio signal. So what exactly is a killer electron, and how does something with less energy than a medical X-ray beam manage to kill a satellite? That question has an answer, and the answer is where this stops being an administrative curiosity and starts being genuinely alarming. Part 4. 2 flares, 2 shocks, and absolutely nothing. Before I take you inside the mechanism, I want to show you what the Sun actually did over the last 2 days, because it is the perfect illustration of the problem. At 15:28, Universal Time on the 26th of July, a sunspot region catalogued as 4494 fired an M3.2 flare. The Space Weather Prediction Center described it in one word: impulsive. It produced a minor radio blackout, an R1, on the sunlit side of the Earth. Then, at 02:43 Universal Time this morning, the same region fired again an M1.0. Both flares did something that gets a forecaster's attention. Each one produced what is called a Type 2 radio sweep. That is a signature of a shock wave moving outward through the Sun's atmosphere, and the frequency drift of the sweep lets you estimate how fast the shock is travelling. The first came in at 1,057 kilometers per second, the second at 622. A shock at 1,000 kilometers per second is not a small thing. An imagery from the stereo, a spacecraft, picked up a coronal mass ejection associated with the first flare beginning at 16:08 Universal Time, about 40 minutes after the flare peaked. Preliminary modelling puts a possible arrival at Earth late on the 30th of July. Modelling for a second possible ejection from the smaller flare is still waiting on imagery. There was also a filament eruption, roughly 14 degrees of it, centred near a position on the northern hemisphere of the Sun at around 02:20 this morning, analysis pending. So, 2 M-class flares, 2 shock signatures, 1 confirmed ejection with an arrival window, and a filament letting go. On paper, that is an active Sun, and the effect on Earth so far is nothing. KP of 2, bezies northward, 14 gigawatts of auroral power, protons at background. The geomagnetic field in the forecaster's own summary was quiet. This is the part of space weather that most coverage gets wrong, and I say that with some sympathy, because the temptation is enormous. A flare happens, it has a dramatic classification letter, it gets written up as a threat, and then nothing occurs and everybody quietly moves on. The reason nothing occurred here is straightforward. Flares produce X-rays, and X-rays affect the dayside ionosphere and nothing else. Whether a flare has any further consequence depends entirely on whether it launched a coronal mass ejection, whether that ejection is aimed at us, and crucially, whether the magnetic field inside it happens to be pointing southward when it arrives. If it is northward, as our local field is right now, the magnetosphere shrugs. Region 4494, for its part, is not building toward anything. It sits at 4 degrees south, 14 degrees west, with an area of 60 millionths of the solar disk and 13 individual spots. Its magnetic classification is beta, and the forecasters note something specific. It has lost the delta configuration it previously had. Delta configurations are where opposite magnetic polarities crowd into the same spot group, and they are the structures that produce the largest flares. 4494 had one. It does not anymore. It is decaying, with a 1% chance of an X-class flare. We covered its predecessor extensively on this channel, the region that dominated the disk earlier this month, in the videos from the 20th and 22nd of July. This one is a smaller, later story, and it is on its way out. So here is the situation, laid out honestly. The Sun did the 2 things over the past 48 hours that reliably generate coverage, and neither of them has produced any measurable effect on Earth's environment. The one thing that is measurably elevated, the one particle population that is genuinely running above an operational threshold right now, is the one that got no coverage at all because it does not have a scale, and it did not have a moment. I think about that inversion a lot. The visible events produced nothing. The invisible one produced the only alert of the last 2 days, and the driver of that invisible one was not a flare at all. It was a hole, not a metaphorical hole, an actual opening in the Sun's atmosphere where the magnetic field, instead of looping back down to the surface, runs straight out into space and lets the solar wind escape at high speed. We spent a whole video on one of these on the 18th of July, when a coronal hole more than 400,000 miles across rotated into an Earth-facing position. That kind of structure produces a stream of fast wind that takes a couple of days to cross the distance and then blows past Earth for days at a time. 2 of those stream arrivals are logged in NASA's own event database this month. One on the 21st of July at 10:11 Universal Time, detected across instruments on multiple spacecraft, linked to an interplanetary shock 5 minutes earlier. A second on the 22nd of July at 2200 hours, detected across a wider instrument set, and that second one carries a linked event in the database. The linked event is a relativistic electron enhancement, catalogued at 1340 Universal Time on the 24th of July. NASA's own catalogue, in other words, formally connects a high-speed solar wind stream on the 22nd to a relativistic electron event on the 24th. Not as an inference by me, as a recorded relationship in the database, 2 days between the stream and the electrons, 4 more days before the flux peaked at 1,160. And now the stream is gone and the electrons are still there. Something in that sequence takes ordinary solar wind and turns a portion of the outer belt into a population of particles moving near the speed of light. And whatever that something is, it is still not fully understood 5 decades after we first started measuring it. That is where we go next, and I need you to hold on to one image before we do. The electrons that crossed the threshold yesterday were, a week ago, part of an unremarkable wind. Part 5. What a killer electron actually is. An electron is the least impressive object in physics. It has almost no mass. It carries 1 unit of negative charge. You have somewhere around 10 to the 28th of them in your body right now, and none of them are doing you any harm. Every electrical device you own works by pushing them along a wire. As a thing to be afraid of, an electron ranks somewhere below a dust mite. What changes everything is speed. When you accelerate an electron to a large fraction of the speed of light, its behavior stops resembling the thing on the wire and starts resembling a bullet. Energy in particle physics gets measured in electron volts, and the convenient definition is that 1 electron volt is the energy an electron picks up, crossing a 1 volt potential difference. The electrons in the wire behind your television are working at a few electron volts. The electrons in a medical X-ray tube are running at tens of thousands. The electrons we're talking about are at 2 million and up. 2 mega electron volts. That is the threshold the GOES 19 sensor is watching, and it is not an arbitrary line. It is roughly where an electron acquires enough energy to punch through the aluminium skin of a spacecraft instead of stopping on it. Below 2 mega electron volts, an electron arriving at a satellite is a surface problem. Above it, the electron is inside. At those energies, the electron is moving at about 98% of the speed of light. Push it up toward 5 mega electron volts and above, which the outer belt does during the strongest events, and you're at 99.6%. These particles cross the distance from the Moon to the Earth in a little over a second. It helps to know how a trapped electron actually moves, because it is not orbiting the Earth in the way a satellite does. It is doing 3 things at once, on 3 completely different timescales. First, it spirals tightly around a magnetic field line, and at these energies that gyration takes something on the order of 1,000th of a second. Second, it slides along the field line toward one pole, gets turned around by the strengthening field near the top of the atmosphere, and slides back toward the other pole, a bounce that takes about 1/10 of a second. Third, and most slowly, it drifts sideways around the planet, taking roughly 10 minutes to complete a full circuit of the Earth. That third motion is the one that matters for our purposes. Because the electrons drift all the way around, a satellite in geostationary orbit does not have to be in the right place at the right time to be exposed. If the belt is loaded, the whole ring is loaded, and every satellite in it is standing in the same weather. The word used for them in the field is relativistic, because at those speeds you cannot describe them with ordinary Newtonian mechanics anymore. Their effective mass increases, time runs differently for them, and when they hit something, they do not deposit energy at the surface the way a slow particle does. They plow through. The other word used for them is killer. As I mentioned, that one is not journalistic embellishment. It shows up in the titles and abstracts of peer-reviewed papers, and it stuck because the people who fly spacecraft needed a term for the specific subset of the radiation environment that ends missions. Now, where do they come from, and how do they get to 2 million electron volts? The raw material is the solar wind, which is not a metaphor either. The sun is continuously boiling off its outer atmosphere, and that outflow washes past Earth at anywhere from 300 to 800 kilometers per second, carrying its own magnetic field with it. Most of that wind is deflected around us by our magnetosphere. Some of it gets in, particularly on the night side, where the stretched magnetic tail can snap and fling plasma back toward the planet. That is the source population. Electrons at a few thousand electron volts, nowhere near dangerous. Getting from a few thousand to a few million is a factor of 1,000 in energy, and that is the part that took physicists half a century to argue about, because there are 2 competing ways to do it, and both of them are real. The first mechanism is called radial diffusion. Think of the magnetic field lines as a set of nested shells around the planet. tighter and stronger as you move inward. A particle trapped on one shell can be jostled inward by fluctuations in the field, and when it moves inward it finds itself in a stronger field. There is a conservation law in this business that says a particle's magnetic moment stays constant as it moves, and the consequence of that law is that moving a trapped particle into a stronger field forces its energy up. Push it inward far enough, and a few thousand electron volts becomes a few million. The transport does the accelerating. The second mechanism is called local acceleration, and it is stranger. Space around Earth is full of plasma waves, and one family of them is called Whistler mode chorus, so named because when you convert the radio signal to audio, it sounds like a dawn chorus of birds. Chorus waves oscillate at frequencies that can match the natural gyration frequency of an electron spiraling along a field line. When the two match, the wave and the particle resonate, and the wave hands energy to the particle. Do that over and over with the right waves at the right place, and you can accelerate electrons in place without moving them anywhere. For decades, the field argued about which of these dominates. The launch of NASA's twin Van Allen probes in 2012 was designed in part to settle it, and the answer that emerged pushed substantially toward local acceleration by chorus waves as the dominant process for the strongest enhancements. Not exclusively. Both processes operate. The balance between them shifts from event to event, and that shifting balance is a large part of why the flux is so hard to forecast. I want to underline what that means for the story we are telling. The hazard with no public warning scale is also a hazard whose fundamental acceleration physics was still being actively contested within the last 15 years. You cannot build a good forecast on a mechanism you are still arguing about, and you cannot build a public scale on a forecast you do not trust. And the Van Allen probes did not just settle an argument. They found things nobody expected, in a region we'd been observing since 1958. It is worth remembering how the belts were found in the first place, because the discovery has the same shape as this whole story. In 1958, Explorer 1 carried a Geiger counter, built by James Van Allen's group at the University of Iowa. As the satellite climbed, the count rate went up as expected, and then, above a certain altitude, it dropped to zero. 0 counts. The obvious reading was that the instrument had failed. What had actually happened was the opposite. The radiation was so intense that the detector had saturated and stopped registering anything at all. The instrument was not blind because there was nothing there. It was blind because there was too much. I find that a useful thing to hold in mind. The first measurement humans ever made of this environment read as nothing, and it read as nothing precisely because the environment was extreme. We have been struggling to see this region clearly from the very first attempt. In 2012, within days of the probes turning on, they detected a third radiation belt. Not 2, 3, a transient storage ring of very high energy electrons sitting between the inner and outer belts, which formed, persisted for weeks, and then was scoured away by an interplanetary shock. 54 years of observing this region, and it produced a structure nobody had ever recorded. Then, in 2014, the same team published something arguably stranger in the journal Nature. Looking at the ultra-relativistic electrons, the ones above about 5 mega-electron volts, they found an extremely sharp inner boundary that those particles simply do not cross. A wall. The paper's title used the word impenetrable, which is not a word physicists reach for casually. The proposed explanation involves exceptionally slow inward transport combined with waves scattering the particles out of their trapped orbits in the cold plasma that surrounds the Earth. But the honest summary is that there is an edge in the radiation belts whose existence surprised the people who study them. So this is the environment we have parked our communications infrastructure inside, a region that was still producing first-time discoveries in the 2010s, a region whose acceleration physics was contested until recently, a region with an unexplained wall in it, and the specific population inside that region, which crossed its alert threshold yesterday, and again the day before, is one that a satellite's aluminium skin cannot stop. Which raises the obvious question. If the shielding does not stop them, what happens when they get inside? Part 6. Charge on the outside. Charge on the inside. There are 2 ways to electrocute a spacecraft, and almost everyone who has heard of the problem at all has only heard of the first one. The first is surface charging. It has been understood since the 1970s, and it is what most people picture when they hear that a satellite got zapped. Lower energy particles, in the range of thousands to tens of thousands of electron volts, arrive at the outside of the spacecraft and stop there. They cannot get through the skin. They pile up on whatever they land on, and because a satellite is a patchwork of different materials with different electrical properties, some of those surfaces charge up faster than others. You end up with a differential. One panel at one potential, an adjacent thermal blanket at another, and a voltage between them across a gap of a few centimetres. When that voltage gets high enough, it arcs. The discharge travels across the surface, and the electromagnetic pulse it generates couples into whatever wiring happens to be nearby. Surface charging is a solved problem, or as close to solved as anything in this business gets. You solve it by making everything on the outside of the spacecraft electrically conductive and tying it all to a common ground, so charge cannot build a differential. Conductive coatings, conductive paints, grounded blankets. Modern spacecraft are designed for it from the first drawing. Surface charging still causes anomalies, particularly in the hours around local midnight when a satellite in geostationary orbit passes through the region where hot plasma gets injected during substorms, but it is a known adversary with known defences. The second way is internal charging, and it is a fundamentally different animal. Internal charging happens when the particles are energetic enough to go through the skin. That is what the 2 mega-electron-volt threshold marks. Above it, an electron arriving at the spacecraft does not stop on the outside. It penetrates the aluminium, passes through whatever is behind it, and comes to rest somewhere in the interior of the vehicle. Where it comes to rest depends on what it hits. If it stops in metal, nothing happens because metal conducts and the charge flows harmlessly away to ground. If it stops in a semiconductor, you may get a transient upset, a bit flip, a momentary confusion, which is a separate and well-studied problem. But if it stops inside an insulator, the charge has nowhere to go. That is the whole hazard, in one sentence. An insulator is by definition a material that does not let charge move. Put charge inside one and it stays exactly where you put it. Spacecraft are full of insulators, circuit board substrate. The dielectric layer inside coaxial cable, the plastic between the center conductor and the outer braid. Potting compounds used to hold components in place and conduct heat away. Cable jackets, connector bodies. Every one of them is a place where a relativistic electron can come to rest and simply sit there, holding its charge, waiting. There is a third failure mode that often gets confused with this one, and separating them matters. A single energetic particle passing through a semiconductor can deposit enough charge in a memory cell to flip a bit, or enough in a power transistor to latch it into a destructive conducting state. That family of effects is called single event effects, and it is caused mainly by protons and heavy ions. It happens instantaneously, and it is designed against with error-correcting memory, redundancy, and radiation-hardened parts. Single event effects are a solved engineering discipline in the sense that everyone knows they exist and everyone budgets for them. Internal charging is not that. Single event effects are one particle, one instant, one bit. Internal charging is trillions of particles, accumulated over a week, in a material that was never meant to hold any of them. The defences against the first do almost nothing about the second, because the second is not an event, it is a dose. Now add more electrons, over hours, over days, over a week of elevated flux like the one running right now. The charge density inside the insulator climbs, and because charge creates an electric field, the field inside that piece of plastic climbs with it. The material is being turned slowly into a capacitor that nobody designed, charged by particles nobody can see, with no path to discharge. There is a number at which every insulating material gives up. It is called the dielectric strength, and it is the electric field beyond which the material stops insulating and starts conducting violently. For common spacecraft dielectrics, that number is in the range of tens of millions of volts per meter, which sounds enormous until you work out how much charge you need to deposit inside a fraction of a millimeter of plastic to get there, and discover that a sustained relativistic electron enhancement can supply it. When the field crosses that line, the material breaks down, a conductive channel punches through it. The stored charge dumps in a fraction of a microsecond. That is an internal electrostatic discharge, and it is happening inside the spacecraft, past all the shielding, past all the surface grounding, right next to the wiring it is about to disturb. I want to give you the analogy that finally made this click for me, And I will be careful with it because analogies in this subject are easy to overreach. Surface charging is static electricity on a doorknob. The charge is on the outside. You can touch the doorknob and equalize it, or you can coat everything in something conductive so it never builds. It is annoying and it is manageable. Internal charging is closer to what happens if you could somehow force the charge into the middle of the plastic handle itself. You cannot touch it. You cannot ground it. You cannot see it. It builds up in there and there is nothing you can do about it except wait and find out whether it lets go. And here is the property that makes this hazard so difficult to see. The property I keep circling back to. The discharge does not have to happen while the flux is elevated. The charge builds during the enhancement. The breakdown occurs when the field crosses the material's limit, and that can be days later, or weeks later, after the solar wind stream has faded, after the flux has dropped back to normal, after every indicator has returned to green. The satellite is carrying the injury around inside it, with nothing on the outside to show for it. That is why the record of this hazard is so patchy. In a world where a satellite failed at the peak of an electron event, everyone would have connected the dots by 1975. In the actual world, satellites fail on unremarkable days, weeks after the event that doomed them, and the operators write down component failure, cause undetermined. The alert that went out yesterday afternoon, the one with serial number 3721, is therefore not a warning that something is about to break. It is a warning that charge is being deposited into places nobody can inspect, on hardware that will not tell anyone what happened to it. So how do you catch a killer that leaves its fingerprints inside a sealed box, in orbit, 22,000 miles up, weeks before the body turns up? Part 7. Lightning. Inside. The insulation. Picture the inside of a communication satellite because most people never have. It is not the sleek object from the artist's impression. It is a box, roughly the size of a small van before the solar arrays unfold, and inside it is packed to a density that would horrify anyone who works on cars. Every cubic centimetre is accounted for. Bundles of cable are laced into harnesses and tied down along structural panels. Circuit boards sit in stacked assemblies. Waveguides and coaxial runs carry signal from the receivers through the amplifiers to the transmitters. Everything is potted, wrapped, insulated and secured because the vehicle has to survive the acoustic hell of a rocket launch before it does anything useful. Now imagine a stream of particles arriving from outside continuously for a week, passing through the outer panel as though it were paper and stopping at random points throughout that interior. Most of them stop somewhere harmless. Some fraction of them stop inside the plastic dielectric of a coaxial cable, in the layer between the signal conductor and the shield. That layer is perhaps a millimetre thick. It is designed to hold off the voltages that a communication signal produces, which are modest. It was never designed to hold off charge injected into its middle from outside. Day 1, the deposited charge is negligible. Day 2, still negligible. Day 4, the electric field inside the dielectric is measurable. Day 7, if the flux has stayed elevated, it is approaching the material's limit, and at some point that we cannot predict, in a particular millimetre of a particular cable on a particular spacecraft, the field crosses the line and the plastic fails. A conductive path opens. Every electron that had accumulated on one side of it rushes across. The current pulse is small in absolute terms, but extremely fast, and fast means broadband, and broadband means it radiates. The pulse couples into the signal conductor a millimetre away. From the satellite's point of view, something just appeared on a line that should have been carrying a clean signal. What happens next depends entirely on what that line was connected to. If it was a data line, the spacecraft may receive a bit pattern it interprets as a command, not a command from the ground, a command from its own damaged insulation. Depending on what the pattern resembles, that could be nothing, or it could be a mode change, a switch throw, a reset. If it was a control loop, the loop may receive a false reading, a sensor value that never happened, a speed signal from a wheel that is not spinning at that speed. If the discharge is energetic enough and close enough to a component, it may simply destroy it. I am describing this in careful detail because I want you to understand what the failure looks like from the ground, which is the thing that has made this problem so slippery for so long. From the ground, there is no explosion, there is no smoke, there is no telemetry channel labelled internal discharge, because you cannot instrument for something that happens at a random point inside a sealed structure. What the operator sees is a satellite that suddenly did something it was not told to do, a momentum wheel that spun down, a transmitter that lost output power, a processor that rebooted, a spacecraft that stopped accepting commands but kept broadcasting. And when the engineers go looking for a cause, they're working from telemetry that records the consequence, not the event. They can rule things out. They can reason backward. In some famous cases, they have narrowed it down to a specific component in a specific control loop. But the discharge itself leaves no direct trace, and the environmental conditions that caused it may have peaked a fortnight earlier. This is why the field ended up leaning so heavily on statistics rather than forensics, and it is why the study I'm going to walk you through shortly matters more than any single incident. There is one more property of internal charging I have not mentioned, and it may be the most uncomfortable one. Shielding does not straightforwardly help. With most radiation hazards you add mass, and the problem gets better. With relativistic electrons there is a complication. When a fast electron is decelerated by passing through material, it emits X-rays, a process called Bremsstrahlung, which is German for breaking radiation. So a shield that stops the electrons converts some of their energy into penetrating X-rays that carry on into the interior. Add too little shielding and the electrons get through. Add more and you generate a secondary radiation field. There is an optimum, and spacecraft designers work hard to find it. And it is not the case that you can simply wrap the vehicle in aluminium and be done. We did not have to guess that any of this was happening. It was demonstrated on an operating spacecraft. In the 1990s, a researcher named Wren analysed telemetry from a geosynchronous satellite, designated DRA-Delta, and produced what the literature describes as conclusive evidence of internal dielectric charging aboard a working vehicle in orbit. The anomalies on that spacecraft did not correlate with the local plasma conditions that drive surface charging. They correlated with the accumulated flux of high-energy electrons, and they clustered after periods when that flux had been elevated for days. That work is a large part of why the greater than 2 megaelectronvolt flux is treated as an operational hazard indicator at all, and why there is a threshold and a bulletin rather than nothing whatsoever. So the alert exists because somebody proved, on real hardware, that the mechanism was real. What never followed was a public scale. The other reason shielding is hard is mass. Every kilogram of shielding is a kilogram of propellant or payload you did not launch. The economics of spaceflight push relentlessly against protection. You cannot prove you needed, and you can never prove you needed it, because the failures you prevented are invisible by definition. So we fly hardware into a particle environment we do not fully understand. With shielding, that is a compromise against a damage mechanism that acts on a delay, and we monitor it with a threshold alert that has no public scale attached. I said at the start that the mechanism was stranger than most people assume, and this is what I meant. The danger is not that the radiation overwhelms the electronics. The danger is that the radiation gets stored quietly in exactly the materials that were chosen because they do not let charge move, and then released at a moment nobody chose. Yesterday's number, 1160, is a measure of how fast that storage is filling, and the wind that filled it has already gone. Part 8. The wind that left and the belt that stayed loaded. The sequence that produced yesterday's alert began on the Sun, and it did not begin with an explosion. Somewhere on the solar disk earlier this month, there was a region where the magnetic field did not loop. On most of the Sun's surface, the field emerges, arcs over and comes back down, trapping hot plasma in the loops and making the bright corona we see during an eclipse. In a coronal hole, the field lines run open, straight out into the solar system, and the plasma that would otherwise be trapped simply leaves. That outflow is fast. Where the ordinary solar wind runs at 300 or 400 kilometers per second, a coronal hole stream runs at 6, 7, sometimes 800. When such a hole rotates into a position facing Earth, that stream sweeps across us for several days, and because the Sun rotates roughly every 27 days as seen from Earth, the same hole can come back and do it again. We spent an entire video on one of these on the 18th of July, when a hole more than 400,000 miles across turned to face us. And what we're seeing in the electron data this week is the downstream consequence of exactly that class of structure. Here is the timeline as the databases record it. On the 21st of July at 10:11 Universal Time, NASA's event catalog logs a high-speed stream detected by instruments aboard multiple spacecraft parked upstream of Earth and linked to an interplanetary shock recorded 6 minutes earlier. On the 22nd of July at 2200 hours, a second high-speed stream event is logged, detected by a wider instrument set including the newer monitors. That second entry carries a linked event, and the linked event is a relativistic electron enhancement, catalogued on the 24th of July at 1340 Universal Time. 2 days from stream to electrons. That gap is not an accident of the record-keeping, it is the physics. The fast wind arrives and compresses the magnetosphere. It carries fluctuating magnetic fields that shake the whole system at a range of frequencies. That shaking does two things at once. It drives the radial transport that can move particles inward, and it excites the plasma waves, including the chorus waves, that can accelerate particles in place. The seed population gets injected during the disturbed conditions. Then the acceleration runs, and it takes time, because you are building energy up in stages. By the 24th, the enhancement is catalogued. By the 25th, the flux peaks at 1077 and crosses the threshold. By the 26th, it peaks higher at 1160. And by today, the 27th, the driver is gone. The solar wind has fallen from roughly 550 kilometers per second to 366. The magnetic field in the wind is down to 5 nanotesla with a northward tilt. The geomagnetic field is quiet. The stream has passed, and the forecast for the electron flux today, in the Space Weather Prediction Center's own words, is that it is likely to reach high levels as the coronal hole high-speed stream effects diminish, with moderate levels then likely tomorrow and the day after. I keep coming back to that sentence because it is such a compact statement of everything that makes this hazard invisible. The effect peaks as the cause fades. There is no alignment between the dramatic part and the dangerous part. Anyone watching the obvious indicators would have logged the 21st and 22nd as a mildly active couple of days, watched the wind slow down, and moved on. The particles that matter did not even reach their maximum until 4 days after that. The 27-day figure deserves a moment of its own, because it turns a one-off event into a schedule. The Sun is not a solid body and it does not rotate as one. The equator turns faster than the poles. From Earth's moving vantage point, the effective rotation period at the latitudes where most coronal holes live works out at roughly 27 days. Coronal holes are long-lived structures. They can survive for several solar rotations, so a hole that swept us with fast wind this month is a reasonable bet to sweep us again next month, and possibly the month after, from the same source at roughly the same interval. Recurring streams are the most efficient loaders of the outer belt there are. A single dramatic ejection delivers one shock and then the system relaxes. A recurring stream delivers days of continuous shaking, then a pause, then does it again before the belt is fully drained. The result is a population that gets topped up on a rhythm, and there is a name for the thing that rhythm produces. The electron flux at geostationary orbit shows a 27-day periodicity that has been visible in the data for decades, which means yesterday's alert is not necessarily a one-off, it may be an installment. Now, does this always happen? That is the question that decides whether any of this is forecastable, and the answer is one of the most quietly devastating results in the field. In 2003, a team led by Jeffrey Reeves published a paper in Geophysical Research Letters with the title Acceleration and Loss of Relativistic Electrons During Geomagnetic Storms. They took 276 moderate and intense geomagnetic storms spanning 11 years, from 1989 to 2000, and asked a simple question. What did the relativistic electron flux do afterward? Roughly 50% of the storms increased it. Roughly 25% produced little or no change. Roughly 25% decreased it. Half. A coin flip, with a quarter of the outcomes being nothing, and a quarter being an improvement. The explanation the authors gave is that storms enhance both acceleration and loss at the same time, and what you observe afterward is whichever process won. Loss is real, and it is powerful. Particles can be scattered into the atmosphere by waves and lost. They can be pushed out through the boundary of the magnetosphere on the sunward side, a process with the excellent name magnetopause shadowing, where the boundary is compressed inward past the orbit of the particles and they simply escape. A strong disturbance can scour the outer belt cleaner than it found it. So a geomagnetic storm is not a predictor. It is a coin toss whose bias depends on details of the solar wind structure that we cannot reliably characterize in advance. Sit with what that means alongside everything else. The one public scale that comes closest to this hazard, the G scale for geomagnetic storms, is at best a coin flip as a proxy for it. You could build a habit of watching for G1 and G2 alerts as a way of anticipating electron enhancements, and you would be wrong about half the time in one direction and a quarter of the time in the other. And in this particular case, the G scale would have told you nothing at all, because no geomagnetic storm was ever declared. KP never got above 2. The flux went above threshold twice anyway. There is a coronal mass ejection with a possible arrival late on the 30th of July. When it gets here, assuming it does, we will have a live test of the Reeves result on this exact belt configuration. It could pump the flux higher, it could leave it flat, it could strip the belt out. Nobody at this moment can tell you which. But if you want to know why any of this is worth 2 days of my attention and yours, it is not the physics. It is what the physics has already done to real hardware, in front of real people, on nights that are documented and dated and still, 30 years later, not entirely explained. The first one took down Canada. Part 9. The night Canada went dark. On the 20th of January 1994, a satellite called Aniki 1 stopped doing its job, and a country noticed. Anik is an Inuktitut word meaning brother, and the Anik satellites were Canada's domestic communications backbone. Aniki 1 and Aniki 2 were the two largest of them, both sitting in geostationary orbit, and between them they carried television distribution across the country, computer data traffic, and telephone service to communities in the north that had no other way of reaching the rest of the world. Aniki 1 failed first. Roughly 9 hours later, Aniki 2 failed as well. 2 satellites, same fleet, same orbit, 9 hours apart. If you were an engineer at Telesat Canada that day, the first thing you would have thought was that something in the design had a common flaw, because the alternative explanation is that the sky itself did it, and in 1994 the sky was not yet a defendant that anyone reached for first. What actually failed on both spacecraft was the momentum wheel control system, and I want to explain what that means, because it is the difference between an inconvenience and a national blackout. A communications satellite is useless unless it points. Its antennas are narrow. The beam that covers a country is shaped like a cone with a very particular cross-section, and if the spacecraft drifts even slightly off attitude, that cone lands somewhere else, and the ground stations designed to receive it find themselves in silence. So every satellite carries a system for holding its orientation, and on these spacecraft that system was built around momentum wheels, heavy flywheels spinning at high speed inside the vehicle, whose angular momentum resists any attempt to rotate the satellite. Change the speed of a wheel and you exchange momentum with the body of the spacecraft, and it turns. On both Aniki 1 and Aniki 2, the circuitry that controls the speed of those wheels went wrong in a very specific way. Investigators traced it to electrostatic discharge damage to a particular part in the speed control loop. The damaged circuit produced a false signal, and the false signal said the wheel was running at full speed when it was not. The control system, obediently believing its own sensor, stopped driving the wheel. The wheel slowed. Eventually it stopped altogether, and when the wheel stopped, the satellite stopped pointing. Aniki 1 was recovered within hours. Aniki 2 was not. Its momentum wheel control was gone, and there was no way to fix a burnt circuit 35,000 kilometers away. The satellite was out of service for approximately 6 months. What happened next is genuinely one of the better engineering stories of the era, and it does not get told often enough. Rather than write the spacecraft off, engineers built a replacement attitude control system on the ground. They used the satellite's remaining thrusters and its telemetry, closed the control loop through the ground station instead of through the failed onboard electronics, and flew the satellite's orientation from Earth. It worked. Aniki 2 went back into service, controlled by a computer that was not on it. That is what it took to recover from a single discharge inside a single component. It is worth understanding why Canada in particular was so exposed, because it explains the shape of the disruption. Canada is the second largest country on Earth by area and one of the least densely populated. Running terrestrial infrastructure to every settlement across that geography is not economic, and in some places is not physically practical. Satellite is not a backup in the Canadian North. For many communities it was the primary link and in some cases the only one. When the pointing failed, what failed with it was not a convenience layer sitting on top of a wired network. It was the network. There is a detail in the aftermath that I think about whenever people describe satellites as robust. The ENIC E2 recovery worked because engineers were willing to treat a satellite as half a machine and supply the missing half from the ground. Every fraction of a second, telemetry came down describing the vehicle's orientation. A computer on Earth worked out what correction was needed. A command went back up, 35,000 kilometers, to fire a thruster. That loop, closed across 70,000 kilometers of round trip, held the spacecraft's attitude steady enough to keep its beam on a country. It is an extraordinary piece of work, and it is also an admission. There was no fixing the damage. There was only building a prosthetic around it. Now, why do we think the Sky did it? Because of what the electrons were doing. The failures occurred during a period of enhanced flux of relativistic electrons, the greater than 2 mega-electron-volt population, the same one that crossed threshold yesterday and the day before. Investigators worked through the alternatives and eliminated everything, except electrostatic discharge, and the environmental conditions pointed to internal charging by radiation belt electrons as the most likely origin of that discharge. The case was strong enough at the time to become one of the standard citations in the field, and then, nearly 2 decades later, it was revisited formally. In 2012, Lamb and colleagues published a paper in the journal Space Weather with the plain title ENIC E1 and E2 satellite failures of January 1994 revisited, going back over the environmental data with the benefit of 18 more years of understanding. Think about what it means that a satellite failure needed revisiting 18 years later. This is not a field where you get a clean answer on the day. The evidence is circumstantial by nature, because the mechanism leaves nothing behind, and the confidence in an attribution can go up or down over decades as the physics improves. There is a detail in the 1994 case that I keep turning over. The 2 satellites failed 9 hours apart. 9 hours is close enough to suggest a common cause, and far enough apart to rule out a single instantaneous event hitting both. That gap is exactly the shape you would expect from the mechanism we walked through. Both spacecraft accumulating charge in their dielectrics over the same days of elevated flux, both approaching breakdown, and the 2 of them crossing the line at slightly different times because no 2 pieces of insulation are quite identical. Not one lightning strike hitting 2 targets. 2 separate glasses, filled at the same rate, overflowing a few hours apart. And on the ground, what people experienced was television going off, data links failing, and telephone service dropping out in northern communities where the satellite was not one option, among several, but the only one. Nobody in those communities was told that a population of relativistic electrons in the outer Van Allen belt had been elevated for the previous several days. There was no reason they would have been. There was no scale, no bulletin they would have seen, and no public vocabulary for the event at all. That was 32 years ago. The vocabulary still does not exist. 3 years later, it would happen again, and this time the satellite would not be recoverable at all. Part 10. Telstar, Midori, and the Zombie. In the Belt. The 11th of January 1997 was the day AT&T lost a satellite it never got back. Telstar 401 carried computer data, telephone traffic, and television programming from geostationary orbit. It was worth somewhere in the region of $200 million. On that day, without warning, it failed completely. Not degraded, not partly recoverable. Gone. The timing is what made scientists sit up. 5 days earlier, on the 6th of January, a solar storm had reached Earth, and the geomagnetic disturbance from it was still running when the satellite died. Researchers at NASA's Goddard Space Flight Center concluded that the geomagnetic activity generated by that storm was the probable cause of the loss. AT&T lost contact with the spacecraft, as one account put it, right in the middle of a magnetic storm at Earth. The American Geophysical Union's own newspaper, EOS, ran a piece on it under a headline framed as a question: Did space weather knock out Telstar and a seismic network? That is an unusual way for a scientific society to phrase things. It tells you that in 1997 this was live, contested and unresolved, and that serious people thought the answer was probably yes without being able to prove it. Notice the pattern repeating. A satellite dies. The environment was disturbed. The attribution is probable, not certain, and it never becomes certain, because the mechanism does not leave a body. 6 years later, the environment did something that removed all doubt about scale, even if it did not remove doubt about individual cases. Between the 19th of October and the 5th of November, 2003, 3 large active regions on the Sun produced 17 flares, including the most intense flare ever recorded by our instruments, along with back-to-back geomagnetic storms at the top of the scale. Because of when they happened, they got a name that has stuck ever since: the Halloween storms. The numbers from that fortnight are the reason space weather is taken seriously as an infrastructure problem at all. According to NOAA's own retrospective documentation, approximately 59% of deep space missions and satellites at all orbits experienced anomalies. 59%. Not a handful of unlucky spacecraft. The majority of everything humanity had flying. The majority of satellites in low Earth orbit were temporarily lost, and re-establishing their positions took several days of round-the-clock work, because the storms heated and expanded the upper atmosphere enough to change the drag on every low-orbiting object and throw the tracking catalogue into confusion. Astronauts on the International Space Station moved into the more shielded parts of the station. Airlines rerouted away from polar tracks toward lower latitudes to keep radiation exposure and communications within limits. Companies running GPS-dependent drilling and marine survey operations cancelled or delayed work. A power grid in Sweden tripped. The mechanism behind that low-orbit chaos is worth a sentence, because it is not what people assume. The satellites were not knocked out of the sky. What happened is that the energy dumped into the upper atmosphere during the storms heated it, and heating a gas makes it expand. The atmosphere puffed outward, and suddenly every object in low orbit was flying through air that was denser than the models expected at that altitude. Drag went up. Orbits decayed faster than predicted. The tracking catalogue, which works by propagating known orbits forward in time, started producing positions that were wrong, and the objects had to be found again by observation rather than calculation. That is the same physics, incidentally, that took down a batch of newly launched satellites in 2022 during a storm that barely registered on the geomagnetic scale, an event we have covered on this channel before. A modest storm, an expanded atmosphere, and hardware that could not climb fast enough through thicker air than it was designed for. And Japan lost Midori 2. Midori 2, formerly ADIOS 2, was an Earth observation satellite launched the previous year. It carried instruments for studying the oceans and the atmosphere, including NASA's Seawind Scatterometer, an instrument reported at around $150 million, designed to measure wind speed and direction over the sea surface. In October 2003, during the storms, the satellite's solar power system failed and the mission ended. A spacecraft barely a year into its working life, carrying instrumentation that took years to design, ended by particles. Then, 7 years later, came the strangest case of all. At 48 minutes past 9, Universal Time on the 5th of April, 2010, a geostationary satellite called Galaxy 15 stopped accepting commands from the ground. That alone would be a bad day. What made it remarkable is what it kept doing. It did not go dark. Its C-band communications payload stayed fully powered and fully transmitting, broadcasting whatever it received, and the satellite, no longer under anyone's control, began to drift along the geostationary belt. The press called it a zombie-sat, and the name was earned. A satellite that is dead is a problem you can plan around. A satellite that is alive, transmitting at full power, and drifting slowly through a belt packed with other people's operating spacecraft is a problem that arrives at each of them in turn. As Galaxy 15 approached each neighbouring satellite, its live transponders threatened to interfere with theirs. It drifted for more than 8 months. Its operator, Intelsat, performed 15 separate flyby procedures, coordinating with other operators and using both its own ground facilities and other companies' teleports to manage the interference as the zombie passed each one. Intelsat's conclusion was that an electrostatic discharge had corrupted the satellite's onboard software, leaving it unable to accept commands while everything else kept running. And here is where I have to be careful, and where I think being careful is more interesting than not being careful. At the time, the industry assumption was that unusually intense solar activity around the 5th of April had triggered the failure. There was a magnetic disturbance that day. The United States Geological Survey maintains a page specifically about the 5th of April, 2010 magnetic disturbance and the Galaxy 15 satellite. The event was written up in the peer-reviewed literature as a space weather case study, under a title that called it another satellite in the wrong place at a critical time. But Intelsat officials stated publicly that the upset had nothing to do with solar activity. That is the operator who had the telemetry saying no. And the company's position has been that the exact cause of the discharge may never be known. So we have a documented electrostatic discharge, a documented geomagnetic disturbance on the same day, a research community treating it as a space weather case, and the operator explicitly rejecting that reading. I am not going to resolve that for you, because it has not been resolved. What I will say is that it is a very clean illustration of why this hazard is so hard to count. Even in the cases where a discharge is confirmed, the attribution to the environment can be genuinely disputed by the people who know the most. The 8-month drift also tells you something about how crowded that ring has become. Geostationary orbit is a single circle, not a volume. Every satellite in it is at the same altitude over the equator, and the spacing between them is measured in fractions of a degree of longitude. A satellite drifting slowly along that circle does not pass through empty space, it passes through a queue, 15 separate coordinated flyby operations, each one arranged in advance with whoever owned the satellite about to be approached, is the operational cost of one corrupted software load on one spacecraft. And every one of those 15 operations happened because of a discharge whose origin the operator says may never be known. 4 cases, 1994, 1997, 2003, 2010. 2 national outages, 1 total loss, 1 mission ended, 1 8-month zombie. 4 cases is not a pattern, it is 4 anecdotes, which is exactly the objection somebody at MIT decided to take seriously. Part 11. 26 failures, 16 years, 1 pattern. If you want to prove that an invisible environmental hazard is damaging hardware, you cannot do it one satellite at a time, because every individual case will always have another explanation. You have to do it with numbers. That is what Whitney Lohmeyer and Kerry Cahoy did. Lohmeyer was a graduate researcher in aeronautics and astronautics at the Massachusetts Institute of Technology. Cahoy was her advisor. Their work was reported in 2013 and published in the journal Space Weather, and the approach was straightforward in a way that most of this field is not. They obtained the anomaly records for 8 geostationary communication satellites, covering 16 years of operation. Within those records, they focused on one specific component, the solid-state power amplifier. Let me explain why that choice matters. A communications satellite receives a weak signal from the ground, shifts it to a different frequency, amplifies it enormously, and transmits it back down. The amplifier is the part that does the amplifying, and it's where almost all of the satellite's electrical power ends up going. Each transponder has one. A large satellite has dozens, and critically, an amplifier failure does not kill the spacecraft. It kills a channel. The satellite carries on, quietly worth less than it was yesterday. That is the perfect thing to study, because it happens often enough to build statistics from, and because it is recorded rather than catastrophic. Across those 8 satellites and 16 years, Lohmeyer and Cahoy identified 26 amplifier anomalies. Then they went and reconstructed the space environment around each one. The reconstruction is possible at all because of something unglamorous that deserves more credit than it gets, the continuity of the measurement. There has been a GOES spacecraft in geostationary orbit counting energetic particles in an essentially comparable way for decades. One retires, another takes over, the calibrations get cross-checked, and the record continues. That unbroken series is what lets a researcher take a failure date from an operator's log and go back and ask what the environment had been doing for the 3 weeks before it. Without that archive, none of this work is possible. You cannot correlate a failure with an environment you did not measure at the time, and you cannot go back and measure it later. The entire statistical case linking these particles to hardware damage rests on somebody having decided, long before anyone needed it, to keep counting and keep the numbers. I mention it because it is the quiet counterweight to the frustration running through everything else in this story. The public communication of this hazard is a blind spot. The measurement of it has been meticulous. They found 3 things, and each one of them lands somewhere important in this story. The first finding is the one I did not expect. Most of the failures occurred during the declining phases of the solar cycle, not at solar maximum. Not during the years of dramatic flares and headline geomagnetic storms. During the descent when the sunspot count is falling, and the public attention that follows sunspot counts is falling with it. The second finding is the mechanism's timescale, and it is the single most useful number in this entire subject. The anomalies occurred at a rate higher than chance would predict, when the greater than 2 mega-electron-volt electron fluence accumulated over the preceding 14 and 21 days was elevated. Not the flux on the day of the failure, the accumulated dose over the previous 2 to 3 weeks. That is the fingerprint of a charging process. If the damage were caused by a single energetic particle strike, the correlation would be with the instantaneous rate on the day. If it were caused by the geomagnetic disturbance itself, the correlation would be with the storm. What they found instead was a correlation with the total number of relativistic electrons that had arrived over the preceding fortnight to 3 weeks, which is precisely what you would predict if charge were building inside a dielectric until it broke down. The third finding closed the loop. The team modelled the amplifier subsystem itself, looking at the dielectric material inside the radio frequency coaxial cables, and asked whether the electric field accumulated in that material over 14 and 21 days of elevated fluence would be high enough to cause the dielectric to break down. It was. So the statistical association had a physical mechanism attached to it, in a specific material, in a specific component, over a specific timescale. That is a complete argument. It is not proof that any particular amplifier died of space weather, and the authors would not claim that it is. It is proof that across 26 failures in 16 years, the failures cluster where the charging model says they should, at rates that chance does not explain. There is a limitation in the study that the authors are open about, and that I should be open about too. 8 satellites and 26 anomalies is not a large dataset. It is what was obtainable, because the anomaly records for commercial spacecraft are not public, and somebody had to be persuaded to hand them over. A physicist studying earthquakes has a global catalogue with millions of events in it. A researcher studying satellite charging has whatever a handful of operators are willing to share, under whatever conditions they attach. That constraint runs right back to the point I made earlier about the record being the visible portion of something larger. The strongest statistical evidence we have that this hazard damages hardware rests on 8 spacecraft, because 8 is how many they could get. And the fact that this remains the state of the art is why an entire research effort has grown up around trying to forecast the greater than 2 mega-electron-volt flux with machine learning rather than physics. There are published models now that train long, short-term memory networks and transformer architectures on years of measurements, trying to predict the flux at geostationary orbit at different lead times, from hours to days ahead. Those models exist because the physics-based forecasts are not good enough to rely on. Nobody builds a statistical black box to predict something they can already calculate. I want to sit with the first finding for a moment longer, because it inverts the intuition that almost everyone carries about space weather, including me, before I started reading for this. The instinct is that danger tracks the sun's activity. Big sunspot numbers, big flares, big risk. Falling sunspot numbers, falling risk. That instinct is correct for radio blackouts, which come from flares. It is broadly correct for radiation storms, which come from particles accelerated by flares and ejections. It is roughly correct for the largest geomagnetic storms. It is wrong for internal charging. And the reason it is wrong is the thing we walked through earlier. During solar maximum, the dominant drivers are eruptions, flares and coronal mass ejections, sudden and transient. During the declining phase, the dominant drivers become coronal holes and the recurring high-speed streams they produce. And recurring streams are the most efficient way there is to keep the outer electron belt topped up. The sun gets quieter in the way the public measures quiet, and simultaneously more persistent in the way that loads the belt. Which brings us back to today. The sunspot number for June of 2026 was 94.4, down 20.2 from a year earlier. The peak in this recent sequence was 133.7 back in August of 2025, and the trend since has been down. By every headline measure, Solar Cycle 25 is on its way out. By the measure that predicts amplifier failures, we are entering the part of the cycle where they happen. And yesterday, for the second consecutive day, the flux that drives them went above its threshold, driven by a coronal hole stream with no geomagnetic storm declared at any point. If Lohmeyer and Cahoy are right about the 14 and 21 day window, The operationally interesting period from this particular enhancement is not today. It runs into the 2nd and 3rd weeks of August, which raises a question I genuinely cannot answer, and neither can anyone else. If a satellite does fail in that window, will anybody ever tell us? Part 12. What nobody has to tell you. There is no law requiring a satellite operator to disclose that their spacecraft was damaged. I want to state that flatly before I go anywhere near the more colourful interpretations of it, because the flat version is already startling enough. When a commercial geostationary satellite suffers an anomaly, the operator's obligations run to their customers, their insurers, and in some cases a regulator concerned with orbital position and radio frequency. Their obligations do not run to the public, and there is no central registry of spacecraft anomalies that anyone can consult. The reasons are ordinary business reasons. An anomaly is commercially sensitive because it affects the perceived reliability of your fleet and your negotiating position with customers. It is insurance relevant, and the attribution can determine whether a claim is paid. It may implicate a manufacturer, which brings contracts and liability into the room, and there is rarely any upside to announcing it. So the record we have, and everything I have walked you through, is the visible portion of something substantially larger. Anik, Telstar 401, Midori 2 and Galaxy 15 are in the public record because they were too big to hide. A national outage, a total loss of a major asset, a mission ending, and a satellite drifting into everyone else's neighbourhood while still transmitting. The failures that were merely expensive rather than spectacular mostly stayed private. This is where a certain reading of the situation becomes very attractive, and I want to give it a fair hearing rather than wave it away, because it deserves one. The claim goes like this. There is a hazard with no public scale. There is a damage mechanism that leaves no forensic trace. There are failures that nobody is required to report. And the one time an operator was directly asked whether space weather killed their satellite, they said no, in public, against the assessment of outside researchers. If you wanted to construct a system in which the true cost of this hazard could never be established, you could hardly do better. Every element of that description is factually accurate, and I still do not think it is a cover-up for reasons I want to lay out honestly. Concealment requires someone to be concealing. The people who publish these studies are, in large part, funded by the same agencies that would have to be participating: NASA, NOAA, National Research Councils. The MIT Amplifier study exists, was published, and is freely citable. NOAA's own retrospective on the 2003 storms is the source of the 59% anomaly figure that makes those storms look so bad. The United States Geological Survey maintains a public page about the magnetic disturbance on the day Galaxy 15 failed. If there is a conspiracy to hide the impact of space weather on satellites, its participants have an unusual habit of publishing the evidence. What actually exists is commercial opacity, which is a different thing and, in some ways, a more stubborn one. Nobody decided to hide this. A lot of separate companies each decided, individually and rationally, that they had nothing to gain by talking, and the aggregate effect is a record with holes in it. The research community works around it the only way it can, by using the anomalies that do get published, by studying government spacecraft whose telemetry is open, and by statistical association across whatever data they can assemble. That is exactly what Lohmeyer and Cahoy did, and it is why their approach mattered. There is a related claim that runs the other way, and it deserves the same treatment. Some people argue the opposite, that space weather gets blamed for failures that were really design faults, manufacturing defects, or operator error, and that pointing at the sky is a convenient way for a company to avoid responsibility. That is also a reasonable suspicion, and it is also sometimes true. The environment makes an excellent defendant precisely because it cannot testify. The honest position sits between the two. Attribution in individual cases is genuinely hard in both directions, which is why NASA scientists could attribute Telstar 401 to a magnetic storm, while Intelsat rejected a solar cause for Galaxy 15, and why the 1994 failures needed revisiting nearly 2 decades later. The claim that survives all of this is the statistical one. Across the anomalies we can see, failures cluster with elevated, accumulated electron fluence at rates chance does not explain. That is a weaker claim than space weather killed this satellite, and a much stronger one than we do not really know. Then there is the second claim, which I see constantly, and which is more fun because it is wrong in an interesting direction. The claim is that the radiation belts themselves are man-made. They are not. The belts were discovered in 1958 by an instrument aboard Explorer 1, 4 years before anyone did anything to them. But the claim is not made up out of nothing, and this is the part worth knowing. On the 9th of July, 1962, the United States detonated a 1.4 megaton nuclear warhead approximately 400 kilometers above the Pacific Ocean in a test named Starfish Prime. Among its many effects, the detonation injected an enormous population of energetic electrons into Earth's magnetic field, where they became trapped exactly as natural particles do. The result was an artificial radiation belt. Reports describe it persisting on the order of a decade, and at its peak it was more intense than the natural belts, and it killed satellites. At least 7 spacecraft were disabled. Telstar 1, the first satellite ever to relay live television, operated normally until November of 1962, when radiation from Starfish Prime caused its command channel to start behaving erratically. On the 23rd of November, the command channel stopped responding altogether. Britain's first satellite, Ariel 1, was damaged. So was Transit 4B. Roughly a third of the satellites then in low orbit were affected. So the honest version is better than the conspiracy version, which happens more often than people expect. Humans did not create the radiation belts. Humans did briefly create an extra one, on purpose, and then watched it destroy a substantial fraction of everything we had in orbit over the following months and years. That is the closest thing to a controlled experiment this field will ever have. Increase the trapped electron population, and spacecraft start dying, on a delay, for years afterward. No one would be permitted to run that test today, and no one needs to, because it was already run. Which leaves the last question, the one that is not about conspiracy at all. Why is there no scale? The answer is not comfortable, but it is not sinister either, and it starts with a decision made about 30 years ago concerning who space weather warnings are for. Part 13, Who the Warnings Were Built For. Somebody had to decide. In the middle of the 1990s, as space weather forecasting matured from a research activity into an operational service, a decision had to be made about how to communicate it. The underlying measurements were and are hopeless as public information. Nanoteslas of magnetic field deflection, watts per square meter of X-ray flux, particle flux units. Nobody outside the field can look at those and know what to do, so the answer was a set of scales modelled on the ones people already understood. 5 levels, minor to extreme, colour-coded, with plain language descriptions of what each level means for ordinary systems and ordinary people. It was, and remains, a good piece of science communication. It took an invisible domain and gave it a vocabulary. And the question that determined which hazards got a scale was, sensibly, this one. Who does this reach? Geomagnetic storms reach a lot of people. They induce currents in long conductors, which means power grids and pipelines, and they light the sky, which means aurora, which means the public looks up and asks what is going on. That earns a scale, and it got 1, the G scale. Solar radiation storms reach people directly. Energetic protons increase the radiation dose received by astronauts and by passengers and crew on high-latitude flights. Airlines make routing decisions based on them. That earns a scale, and it got 1, the S scale. Radio blackouts reach people who need to communicate. Flares ionize the dayside upper atmosphere and high-frequency radio stops working, which matters to aviation, to maritime operations, to emergency services, and to anyone whose navigation depends on low-frequency signals. That earns a scale, and it got 1, the R scale. Now apply the same question to relativistic electrons. Who does this reach? It reaches spacecraft. Specifically, it reaches the interior dielectrics of spacecraft in and near the outer radiation belt. It does not increase anyone's radiation dose on an aircraft. It does not induce currents in a pipeline. It does not produce an aurora. Its total population of directly affected parties, worldwide, is measured in hundreds of people, all of them professionals, all of them reachable by a mailing list. Given that framing, the decision not to build a public scale was reasonable. It might even have been correct at the time, and I think it has quietly become wrong without anyone doing anything wrong. Because the framing assumed that a hazard which only reaches spacecraft is a hazard that only reaches spacecraft operators. In 1995, that was nearly true. Satellite services were an important but bounded part of the economy. Losing a transponder was a commercial event that stayed commercial. That assumption has not survived. the number of active satellites has increased by roughly an order of magnitude in a decade. Financial systems take timing from space. Agriculture runs on positioning from space. Aviation and shipping navigate by it. Broadcast, backhaul, remote medicine, disaster response, and a growing share of ordinary consumer internet all route through hardware in orbit. The set of people who experience the downstream consequences of a satellite failure is no longer a few hundred professionals. It is effectively everyone, arriving indirectly, delayed, and unlabeled. It is worth being specific about what that dependence actually looks like, because everything runs on satellites is the kind of sentence that slides past without landing. The positioning signals that most people associate with finding a restaurant are, in engineering terms, timing signals. Each satellite broadcasts an extremely precise time, and a receiver works out its position by comparing the arrival times from several of them. That timing is used directly on its own, by systems that are not trying to find anything. Financial trading venues use it to timestamp transactions so that the sequence of events can be reconstructed and regulated. Telecommunications networks use it to keep cell towers synchronized so that handovers work. Electrical grid operators use it to time measurements of the phase of alternating current at different points on the network, which is how you detect instability before it becomes a cascade. Agriculture uses it for machine guidance to a few centimeters. Aviation uses satellite-based augmentation for approaches. Shipping uses it for navigation and for the automatic identification transponders that keep vessels from running into each other in fog. Emergency dispatch uses it to route ambulances. None of those users think of themselves as satellite operators. All of them stop working properly if the space segment degrades. And then there is everything in geostationary orbit specifically. The television distribution feeds that carry a broadcast from a studio to the local transmitters. The backhaul links that connect remote networks to the wider internet. The maritime and aviation connectivity services. The government and military communications. And the emergency communications that get deployed after a hurricane precisely because the terrestrial infrastructure is gone. That is the population standing behind the amplifiers that Lohmeyer and Kerhoy were counting failures in. So the scale that was never built for excellent reasons, and the world it was reasoned about has been replaced. We have always been told that the warning systems will tell us when something dangerous is above us. But what if the warning system is telling the truth, completely and accurately, about a set of dangers that was defined before the thing we most depend on existed? I want to be careful not to overstate the criticism, because there is a genuine counter-argument, and it is not weak. A public scale for electron flux would be, for almost everyone who saw it, an actionable-looking number about which they can do precisely nothing. You cannot shelter from it. You cannot reroute around it. You cannot turn anything off. Publishing a 5-level color-coded severity index for a hazard whose only mitigation lies in spacecraft design and operator procedure could easily produce more noise than understanding, and space weather communication already fights a losing battle against people reading every M-class flare as an incoming apocalypse. That is a real argument, and I do not dismiss it. My objection is narrower. It is not that the public needs a number to act on. It is that the absence of any public representation at all has produced a situation where a category of infrastructure damage that has been running for over 60 years is invisible to the people whose lives depend on the infrastructure. Not misunderstood, not underestimated, absent. You can check the space weather every day for a year, do it conscientiously, use the official sources, and never once encounter the existence of the hazard that has plausibly ended more commercial spacecraft than everything else on those pages combined. It is fair to ask what the alert is actually for, if not for the public, and the answer is that it does real work inside the operations rooms that receive it. An operator who knows the flux is elevated does not stop flying the satellite because you cannot. What they do is change how they fly it. Non-essential commanding gets deferred. Planned maneuvers and reconfigurations, the operations that involve switching things on and off and moving power around inside the vehicle, get pushed to a quieter week where possible, because a transient arriving during a switching operation is far more likely to be interpreted as a real command than one arriving into a stable system. Anomaly investigation gets primed. If something odd happens over the next fortnight, the environmental data is already in hand, and the charging hypothesis is already on the table, rather than being reconstructed months later. That is a genuinely useful product. It is just a product with an audience of specialists doing specialist work, on behalf of a public that is not in the conversation. That is the thing I cannot get comfortable with. Not a cover-up, a blind spot built into the instrument panel on purpose, for reasons that made sense at the time, and the blind spot is about to be pointed at the part of the solar cycle where this particular hazard does its best work. Part 14. The Era of Holes. The Sun is winding down, and that is the dangerous part. Solar cycle 25 is past its maximum and descending. You can watch it happen in the monthly sunspot numbers. In June of 2025, the smooth count was 114.6. It climbed through the summer to 125.9 in July, then 133.7 in August, which is the high point of this recent sequence. Then it began to fall, 129.7 in September, 114.8 in October, 91.7 in November, a bounce back to 124.2 in December, 115 in January of this year, then a sharp drop to 77.4 in February, 86.6 in March, 79.3 in April, a recovery to 101.5 in May, and 94.4 in June. 94.4, down 20.2 from a year earlier. The radio flux at 10.7 centimeters, which is the other standard measure of solar activity, tells the same story, sitting at 138.21 for June against readings in the 150s and 160s last year. Every public signal from that data says the same thing. The risk is falling. The exciting part is over. And what that data does not say, because it was never designed to, is that the Sun is changing which weapon it uses. At solar maximum, the drama comes from eruptions. Complex sunspot groups with tangled magnetic fields build up energy and release it suddenly, as flares and as coronal mass ejections. Those events are dramatic, brief, and largely transient in their effect on the radiation belts. They can load the belt and sometimes they scour it. Half the time up, a quarter flat, a quarter down, as Reeves and colleagues showed. During the declining phase, something different becomes dominant. The Sun's large-scale magnetic field reorganizes, and big, stable coronal holes open up, often extending from the polar regions down across the equator. These are the structures we spent a whole video on the 18th of July, when one of them stretched more than 400,000 miles and turned to face us. They are long-lived. They rotate with the Sun and come back around roughly every 27 days, and they keep coming back for months. The history of how we worked out what these things were is one of my favourite stories in the whole of solar physics, and it is directly relevant, because it is another case of a hazard being visible in its effects for decades before anyone could see its cause. In the 1930s, a German geophysicist named Julius Bartels was studying magnetic disturbance records and noticed something regular in them. Certain disturbances recurred on a 27-day cycle, over and over, matching the rotation period of the Sun as seen from Earth. Something on the Sun was coming back around and doing it again. He could see the rhythm perfectly clearly in the data. What he could not do was find the source. There was nothing visible on the solar disk in the right place. No sunspot, no bright region, nothing. So he gave the invisible sources a name that was really an admission. M regions, M for magnetic, meaning the thing responsible for these recurrent magnetic disturbances, whatever it turns out to be. The M regions stayed unidentified for about 40 years. The answer arrived in 1973, when the crew of Sky Lab operated an X-ray telescope pointed at the Sun and produced images of the corona from above the atmosphere. In X-rays, the hot looped corona glows brightly, and the open field regions, where the plasma has escaped rather than been trapped, appear as darkness. The images showed enormous dark patches on the solar disk, and when those patches lined up with the Earth, the recurrent disturbances followed. Bartels' M regions were coronal holes, invisible in visible light, obvious in X-rays, and responsible for a rhythm in Earth's magnetic field that had been recorded for 4 decades without an explanation. I bring that up because the shape of it is exactly the shape of the thing we're talking about now. A real, repeating, measurable effect driven by a cause that our instruments were not built to see, named after our own ignorance until the technology caught up. Each pass sends a stream of fast solar wind across the Earth for several days. And streams, unlike eruptions, are patient. There is one more piece of the mechanism that explains why a stream of wind, which sounds gentle, shakes the magnetosphere so effectively. The fast wind from a coronal hole does not travel through empty space. It travels into the slower wind that left the Sun ahead of it, and it catches up. Where the fast wind piles into the slow wind, you get a compression, a region of enhanced density, an enhanced magnetic field moving outward, correlating with the Sun. The technical name is a correlating interaction region, and it is the leading edge of the stream that does most of the damage. When that compression sweeps past Earth, the magnetosphere gets squeezed and then held in a state of continuous buffeting for days as the fast wind behind it keeps blowing. That sustained buffeting is what generates the wave activity, including the chorus waves, that accelerates electrons in place. It is a slow, grinding process compared to the sharp hammer blow of an ejection arriving, and slow grinding is precisely what a charging problem wants. That patience is exactly what loads the outer electron belt. A single shock gives the system one hard shake and then lets it relax. A recurring stream shakes it for days, pauses, and shakes it again before the belt has drained, and the electron population ratchets upward. This is why the flux at geostationary orbit shows a clear 27-day rhythm in the long-term data, and it is why the declining phase of every solar cycle is the phase in which recurrent streams dominate the radiation belt environment. Now put that next to what Lohmeyer and Cahoy found. Most of the amplifier anomalies in their study occurred during the declining phases of the solar cycle. Those two facts are the same fact, seen from two directions. The declining phase is when coronal holes take over. Coronal holes drive recurring streams. Recurring streams load the outer belt. A loaded outer belt drives internal charging. Internal charging kills amplifiers, and the public measure of solar risk, the sunspot number, is falling the entire time. We are in that phase now. This week's enhancement was driven by exactly this machinery. A coronal hole stream arriving around the 21st and 22nd of July, an electron event catalogued on the 24th, threshold crossings on the 25th and 26th, and a forecast of continued high levels today even as the stream decays. No geomagnetic storm, no public scale reading, no coverage. If the hole responsible is a long-lived structure, and most of the large ones are, then it should rotate back into an Earth-facing position around the third week of August. That is a real, checkable prediction with a date attached, and I intend to check it. There is one more layer to this that I want to raise carefully, because it is speculative, and I will label it as speculation rather than let it drift into sounding like a finding. Earth's magnetic field is weakening. We covered this in detail on the 17th of July. The global dipole has been declining, and the South Atlantic anomaly, the region over the South Atlantic and South America where the field is weakest, has been growing and has been observed splitting into two separate minima. Over that region, the inner radiation belt reaches down to remarkably low altitudes, which is why spacecraft crossing it experience elevated particle rates, and why some of them shut down sensitive instruments as they pass through. The trapped particle population is shaped by the field that traps it. If the field is changing, the geometry of the trapping changes with it. What I do not know, and what nobody can currently tell you with confidence, is whether that shift moves the internal charging hazard in any operationally meaningful direction over the coming decades. It is a legitimate open question rather than a prediction. But it sits underneath everything else in this story, a hazard we do not fully understand, in an environment we're still discovering new structures in, contained by a field that is measurably changing, with more of our hardware inside it every year. And through all of that, the instrument panel still has 3 rows on it. Part 15. The Storm with No Name. Let me bring this back down to the number 1160, recorded at 17:05, universal time yesterday, by a sensor on GOES 19, 35,786 kilometers above the equator, against a threshold of 1,000, following 1,077 the day before. That is not a large enhancement by historical standards. I want to be completely straight with you about that, because the temptation in a story like this is to inflate the immediate event to match the significance of the pattern, and I would rather do the opposite. The outer belt has produced flux levels many times higher than this. During the largest events, it goes to tens of thousands of particle flux units. Yesterday's reading crossed the operational line by about 16%. What makes yesterday worth all of this attention is not the size. It is the structure of the situation it reveals. A modest enhancement of the most damaging particle population we know about, driven by a coronal hole stream rather than a storm, peaking after its driver had already faded on a day when the geomagnetic field was quiet. The solar wind was slow, the interplanetary field was pointing the wrong way to do anything. The aurora was running at a quarter power, the protons were at background, and all three public scales read 0. Nobody was told because there is no mechanism for telling anyone, and if it does damage, the damage will happen somewhere in the next 2 to 3 weeks, inside a sealed box, in a material chosen specifically because charge cannot move through it, at a moment nobody will be able to identify, on a spacecraft whose operator has no obligation to say anything, and several good reasons not to. That is the whole shape of it. A cause with no visibility, an effect with no timestamp, and a record with no requirement to exist. Let me put the whole week back together in order, because seen as a sequence it is almost absurdly undramatic, and that is the point. Around the 21st of July, a high-speed stream from a coronal hole reaches Earth, logged in NASA's database at 10:11 Universal Time, with an interplanetary shock 6 minutes earlier. On the 22nd at 2200 hours, a second stream event is logged. The magnetosphere is buffeted. Nothing newsworthy occurs. There is no major geomagnetic storm, and nothing about those 2 days would have made a headline anywhere. 2 days later, on the 24th at 1340 Universal Time, a relativistic electron event is catalogued, formally linked to the stream. Still nothing newsworthy. On the 25th, the flux peaks at 1077 and crosses the threshold. An alert goes out to a mailing list. On the 26th at 1705 it peaks higher at 1160. Another alert. Same mailing list. Meanwhile, the Sun fires an M3.2 flare with a shock at 1057 km per second, which is the event that would have made the news if anything had, and it produces no measurable effect on Earth's environment whatsoever. And today, the 27th, the solar wind has fallen to 366 km per second. The magnetic field is quiet, the aurora is at 14 gigawatts, all three scales read 0, and the electron flux is forecast to remain high as the stream that caused it fades away. 6 days, 2 threshold crossings, 1 flare that got attention and did nothing, 1 particle population that got no attention and did the only thing that happened. Now let me widen this out because I think the pattern here is bigger than satellites. We have built a civilization whose critical systems are increasingly invisible to the people who depend on them, not hidden. Invisible in the more ordinary sense, too specialized to be reported on, too indirect to be felt, too slow to make a moment. The satellite in geostationary orbit that carries a timing signal into a financial network is a piece of national infrastructure that almost no citizen of any nation could name, describe, or find. Its failure would not look like a failure. It would look like an unrelated inconvenience somewhere downstream, 3 steps removed from the box that actually broke. And the environment that threatens it is invisible in the same way. It has no weather. It produces no light. It is a change in the number of very fast electrons drifting around the Earth in a ring, and there is no window you can look out of that will ever show it to you. Go further out, and the pattern is older than any of our technology. This planet has always sat inside a stream of charged particles from the Sun. The Van Allen belts have been there for as long as Earth has had a magnetic field, and the field has been there for billions of years. That field is the reason there is an atmosphere to breathe and an ocean to swim in, because it deflects the wind that would otherwise have stripped both away over geological time. The same structure that made this planet habitable also stores, in its outer regions, a population of particles moving so fast that we cannot shield against them economically. The shield and the hazard are the same object. It has always been that way. It only became a problem when we started putting things inside it. Think about the timescales involved, because they are wildly mismatched, and I do not think we have really absorbed what that mismatch means. The magnetic field has been trapping particles above this planet for something on the order of 3 billion years. Every organism that has ever lived has lived underneath it, protected by it, and entirely unaware of it. Nothing on the surface has ever needed to know that the belts were there. We have been putting hardware into that environment for 68 years. That is a rounding error against 3 billion. And in that rounding error we have gone from 1 Geiger counter that read 0 to a dependence so complete that a continent's telephone service can be interrupted by a discharge inside a millimetre of plastic. The environment did not change. Our exposure to it went from nothing to total in less than a single human lifetime, and our system for telling people about it was designed in the middle of that transition based on who was affected at the time. 68 years ago, a Geiger counter on Explorer 1 climbed into that region and read 0, and the 0 meant the opposite of nothing. We have been misreading this environment in one way or another from the very first measurement. We built a scale for the parts of it that hurt people. We did not build one for the part that hurts the machines that people now cannot function without. And in the years since, the machines have quietly become the part that matters. Yesterday the count went to 1,160, and a computer wrote a line of plain text with a serial number on it and sent it to a mailing list. The stream that caused it is already gone. The particles are still there. They will decay over the coming days, and the flux will drop back below threshold, and the whole episode will close without anyone outside a small professional community ever having known it happened. Unless it comes back. Because if the coronal hole that produced this is one of the long-lived structures that dominate a declining solar cycle, it is going to swing around the far side of the sun and return to face us, and the calendar for that is not vague. It is 27 days. So here is the question I'm going to be watching for, and the one I would like you watching for too. Around the third week of August, does the greater than 2 mega-electron-volt electron flux at geostationary orbit cross 1,000 particle flux units again on schedule from the same hole? Because if it does, this was not an event, it was an installment